Okay, so we're moving into chapter 11 and we're starting off with simplifying rational expressions. So what I'd like you to do, if you haven't done so yet, is get out a blank sheet of paper and take these notes along with me. It's super important that you guys are working through these problems as I'm working through them. So pause the video when you need to, rewind when you need to, and let's learn some math. Okay. So with simplifying rational expressions, first of all, a rational expression is something in fraction form. So I'm just going to jump right into it with some examples, and I'm going to start by reviewing what you guys learned all the way back in Math 1. So let's start with a simple example, and let's write. So in Math 1, you guys talked about this concept of the giant 1. And the giant 1, so I'm going to write it x over x times y over z. And if I was simplifying this, I could think of x over x as 1 because anything divided by itself is 1. So in the Math 1 book, they would draw a 1. I'm not good at drawing the giant 1. To help us visualize why x over x, what we would typically say is x over x, they cancel out. But the real idea behind that is that anything divided by itself equals 1. So really we just have 1 times y over z, which is y over z. So we're going to use that same concept and build onto it with a little more complex types of fractions. So let's look at one more. We'll call this example A from number 1. Let's look at one more kind of like that. All right, so let's say we had 3xy divided by 2y. So in Math 1, I know I'm going back here a little bit, but we can break apart fractions as well as in the same way that we can multiply them together. So let me just do a quick example up here. Just like I could do 1/2 times 3 over 5, I could rewrite that as a single fraction by multiplying the 1 and 3 together and multiplying the 2 and 5 together. So I could do that and write that as 3 over 10, or you can go backwards and break them apart. I could take this 3 and rewrite it as 1 times 3, and I can rewrite 10 as 2 times 5 and break it into 2 fractions. So you can go either way with that. So this is all in part B a single fraction here, but we could think of it as splitting it up into 3x over 2 times y over y. And the only reason I'm doing that is to reiterate that giant 1 idea. So really this is just 3x over 2 times 1, which is 3x over 2. So all of this work right here isn't totally necessary to write out. I just want to be really clear about what's happening with these y's before we move on and start making problems a little tougher. So typically what we would do when you're looking at this problem as it is right now, what I would do is just recognize that y over y, and I cross them out and say they cancel out because y over y is 1. And then I would jump right to my last line of writing the answer. So this is just a quick review of that giant 1 and why something divided by itself equals 1. Okay, I'm going to do another example here involving exponents. So it's the same idea, but we're going to kind of extend that. So let's say I had x cubed divided by 3x squared. Now I know that we've learned properties of what to do here with these exponents if I have the same variable raised to a power, but I just want to show you this in the same way you were introduced to the idea in Math 1, just to get us all on the same page. So we know x cubed is actually x times x times x. It's x times itself 3 times. And then I have this 3 right here, so that's just still 3. And then I can write x squared as x times x. So if we look at what we have here, I could technically break these apart, and I could rewrite this as I could take that, I have these x over x's and these x over x. So I've got x divided by x times x over x times, and then this last one, x over 3. We know x over x is 1, x over x is 1, times x over 3, so we have just x over 3 remaining. How could we have done, again, these steps right here aren't totally necessary at this point, so you guys should be getting a little faster at this and moving from here to here. So let's see how we would think about that. Well, we've got x cubed and x squared, and the result when you've got the same base is always the difference between the exponents, because 2 of these 3 x's cancel out with these 2 down here. So the result is whatever's left. So 3 minus 2 is 1, and that's why we have x to the first remaining in the numerator. So I'm hoping that you guys are getting to a point where you could go straight to recognizing this 3 and this 2 means we'll be left with x to the first in the numerator, because that's where it was larger up here, divided by 3. So just a little bit of review on some of these concepts before we get into some more complicated problems, which we'll do right now. So let's look at another example, and we're going to kind of beef up the fractions that we're looking at. All right, so let's get into some new stuff. All right, so example A, let's do x minus 2 over x minus 2 times x plus 5 divided by x minus 1. So we've got two fractions being multiplied together here. So the first thing I want to point out is both of these fractions, each fraction has x in both the numerator and denominator. So what I'm about to show you right now is probably the number one mistake I see across the board at all of my classes, any content level in terms of grade. I always see people canceling out these x's, and we just can't do that. Because think about what's happening in these fractions. Before you're dividing, what am I doing to x right here? Before I take this numerator and divide it by this denominator, the first thing I'm doing is subtracting 2. So I can't cross out these x's with each other because there's something else that I'm doing before I divide, and that's why we don't really typically write it like this, but these are actually considered to be in their own group of parentheses. So don't fall into that trap of wanting to cancel out x's wherever you see them, because these are actually, it's this whole numerator divided by this whole denominator. Now these are the same, x minus 2 divided by x minus 2. So regardless of what x is, these two entire fractions, or these two entire numerator and denominator, those do cancel out because anything divided by itself is 1. However, in this second fraction, a lot of people right here want to cancel out the x's, and that's just not how it works. Let's try and plug a number in here. If we said x equals 2 and we want to check it, so that would be 2 plus 5 divided by 2 minus 1. So that would be 7 over 1, which is 7. So that's what would happen when I plugged 2 in here. If I just canceled out these x's and said, oh, those are canceled, I would end up with 5 over negative 1, and that's negative 5, which is not the same as what would actually happen when I plugged a number in. So this is just an example of how this fraction works when I actually plug a number in, and why I can't just cancel out these x's. Because before I divide, I'm adding 5 in the numerator and subtracting 1 in the denominator, and then the division happens. So this actually, what we're left with, is the result of x plus 5 over x minus 1. That's just the answer. So we can't simplify that anymore. And now I'm going to introduce something a little new, at least for us. I'm not sure if you guys did this in Math 2 or not. But if I'm looking at this, this is my result after I simplify my original expression here. But now that we're dealing with fractions, which introduces variables that cause problems or variables that we could not plug in, it is important that we state any restrictions on what can or can't be plugged into this expression. So with fractions, we know we can't divide by 0. So we need to figure out what values of x would cause us to divide by 0. I could plug in 0 for x, because then I would just have 0 minus 1, which is -1, which is totally fine because then we're not dividing by 0. But when I plug 1 in for x, then I would have 0 in the denominator. So this means x cannot be 1. So this is the restriction on x. So in your homework, I believe it says state the restrictions. This is a restriction on x because we can't plug 1 in. So we're restricted. So we kind of state what that restriction is here, and it's always the numbers that we cannot plug in because it would force the denominator to be 0, and we can't divide by 0. All right, let's look at another example for simplifying rational expressions. Okay, this one might seem pretty simple. It is in some ways, but it just helps me explain another concept to you guys. So 9 over x times x over 9. So again, I'm going to kind of show the longer way of thinking about this and then get into the shorter version of thought that I want you guys to start having here. So first of all, I could rewrite this as a single fraction by multiplying my numerator and multiplying my denominator. So that would be 9 times x, which is 9x in the numerator, x times 9, which is also 9x in the denominator. So now we've got 9x over 9x, which we know anything divided by itself is 1. Could we have gotten there from the very beginning? Yes, because multiplication is what we call commutative, and that means you can reverse the order. Since we know that to multiply fractions, you just multiply the top and bottom together, before we even combine these to this single fraction, you can recognize that, okay, I could technically, when I multiply these together, really all I'm doing is just multiplying the 9 times x, and think of it already as a single fraction. Then you've got, this is a dot for multiplication, then you've got 9 times x over x times 9. I can recognize, okay, these are going to cancel out, and these are going to cancel out because of that multiplication right here. So if this had been, if these had been any other operations besides multiplication, we couldn't do this. But we can. So we can recognize 9 over 9 will cancel, x over x will cancel. That does not mean the answer is 0 just because everything cancels out. It's not canceling out. It's actually we're recognizing where we're multiplying by 1. So this problem is actually just taking this, which simplifies to 1, times this, which simplifies to 1, which equals 1. So that's just another way of showing how some of these cancellations work. And before I move on, it's also worth stating that restriction, because even though my answer simplifies to 1, I still had x in the denominator at some point. So even though there's no x in the denominator here, we still need to state that x cannot be 0. Because that's a restriction on our original expression here. And actually, while I'm talking about that, let me back up to part A, because I forgot to mention, so in this final simplified expression, we saw that x cannot be 1, but I forgot to add another restriction, because even though this x minus 2 over x minus 2 isn't a part of our final answer, it was a part of our original expression, which means we cannot use 2 as a value of x either, because then this fraction would have been 0. So I need to add on to my restrictions, x cannot equal 1 or 2. So those are my restrictions on x for part A, and then in part B, x cannot be 0. All right, so let's move on to a new one, part C. Okay. So let's see, a new expression here. I've got 2m minus 5 in parentheses times m plus 6 in parentheses. That whole thing is over m plus 6 times 3m plus 1. So there's a lot going on here. So once you get this written down, take a look at it. we've got multiplication in both the numerator and denominator. And hopefully you're recognizing I've got this m plus 6 over m plus 6 here. So multiplication is commutative. And what I mean by that, I've said it already. It means that, I'm just going to draw a little extra box over here. A times B equals B times A. We can reverse that. 2 times 3 is the same as 3 times 2. It doesn't matter with multiplication what order you multiply. You'll always get the same result. That means I can think of this as I can reverse the order here of my numerator or denominator, however you want to think of it, and switch those up. And then I would have m plus 6 times 2m minus 5 over m plus 6 times 3m plus 1. So hopefully now you're recognizing this m plus 6 over m plus 6. Anything divided by itself equals 1. So those do that canceling out, and we're left with our final answer of 2m minus 5 over 3m plus 1. Now, this is the point where a lot of people want to do this. There's an m there, there's an m there, let's cancel out. That is not how it works. Remember, this is one of the biggest mistakes I see across the board, is canceling out things like that just cannot be canceled out. I can't do that first, because before I'm not dividing m over m and then doing all this other stuff. First I'm multiplying by 2, then subtract 5, and then that entire numerator is divided by the denominator, 3m plus 1. I can't divide m over m first. We have to follow the fact that this numerator is in its own sort of parentheses up here, and same with the denominator. So this is our answer, and some of you probably would have gone straight from our original to the answer, and that's good. That's what I want you to get to, because you have hopefully recognized right away, I've got m plus 6 here and here. You know that you can switch them around to make them, right on top of each other, but you don't have to write it like that. We can recognize from the beginning that these are going to cancel out with each other, and that it's going to leave 2m minus 5 divided by 3m plus 1. So this is our final result, but we do need to talk about restrictions. So there are values of x that we cannot plug in here, because we need to think about when this entire denominator will equal 0. And if you're not sure, then write it out as an equation. So we know that the restriction is going to be when the denominator equals 0. So that's when 3m plus 1 equals 0. That's going to be our restriction on m. So we know that in order for this expression to work, this denominator cannot equal 0. So then solve for m. So we would subtract 1 from both sides, and we would get 3m cannot equal negative 1, and then divide by 3 on both sides, and you get that m cannot equal negative 1/3. If it does, then the denominator would equal 0. So that's how you would get your restriction. But we need to go back to the original, because m plus 6 was a part of the original denominator, which means negative 6 also is a restriction. So negative 1/3 and m also cannot equal negative 6. So it's worth discussing that as well. All right, let's keep rolling. Let's look at another example here. Example D. Gonna switch it up a little bit, and let's see, 6 times n minus 2 squared over 3 times n minus 2. Okay, so there's a couple things we can do here. The first one I'm hoping you saw is we've got 6 times something divided by 3 times something. That means we can think of this 6 over 3 as its own fraction, which we know simplifies to 2. Because 6 divided by 3 is 2, 3 divided by 3 is 1. So really what we've got is 2 remaining in the numerator, n minus 2 squared over n minus 2. Now, instead of writing it as n minus 2 squared, I'm actually going to write it out like in this expanded form. So n minus 2 squared is n minus 2 times n minus 2. The reason I'm doing that is so that you guys can see when I do this cancellation with n minus 2 over n minus 2, then I have 1 remaining up here. So my final answer would be 2 times n minus 2. And what's remaining in the denominator? That would just be 1, because when I do the cancellation, this divided by this whole thing equals 1. So it's really 2 times n minus 2 divided by 1, but we don't have to write that divided by 1 because that would just result in this final answer. Could you go straight from this to this final answer? And that answer is yes, because we know what to do when I've got the same base down here, n minus 2 with a power of 2, over n minus 2 with a power of 1, we subtract 2 minus 1, which results in n minus 2 to the first. So you don't have to expand it and do that cancellation here. Again, I just go through that process so you guys can see why we have this 1 n minus 2 remaining, this whole thing. Now the last thing here is to talk about the restriction here. There's no denominator in my final answer, but there was one in our original expression, so we still have to talk about the restriction. And that denominator would equal 0 when n equals 2, because then you would have 2 minus 2. So the restriction is n cannot equal 2. Okay, let's look at another example here before we move on to one more type of problem. All right, so this will be a pretty fast one. So we've got a numerator of 3 minus 2x divided by 4x minus 1 times 3 minus 2x. So I've got 3 minus 2x in the numerator, I've got 3 minus 2x in the denominator. So we know that those are we know 3 minus 2x divided by itself is 1. So I know that these are going to cancel out, as we say. But I'm doing this problem just to highlight that one of the common mistakes I get is that people often forget that when this cancels out, they think, oh, there's nothing there, so my numerator is now 0. But that is wrong, because it's not that there's nothing here, it's that I have 1 over 1 now. So our numerator results in 1, not 0, and the denominator still has this 4x minus 1. So this is the result for that. We do need to talk about the restriction though. And again, if your denominator is got a little more going on than typical, and you're not sure what value of x would make the whole thing equal 0, then just set it up as an equation, because we know that this whole denominator, 4x minus 1, cannot equal 0. Add 1 to both sides, so we know 4x cannot equal positive 1. And then divide by 4, which means x cannot equal 1/4. So this is our restriction on x for that one. Okay, so we're going to do one last set of problems here and kind of put together what we know now about simplifying expressions and combine that with factoring. So I think this is example 4. I might be off. Simplify and state restrictions. So these are going to look different, these problems, just a little bit. All right, so let's see, for A, we've got x squared plus 6x plus 9 divided by x squared minus 9. Now already this problem looks different from the other ones we've done in this section because we don't have it in factored form. So if we look back up to E, we've got this denominator, it's got 2 factors. It's already in factored form rather than in the way it would typically look if we multiplied it out. That would be a quadratic. So if we look in example A, we've got a quadratic divided by a quadratic. That is a big red flag to factor first. And if anything, when you're simplifying expressions, the first thing you're going to do, if you can, is factor. Because when it's in factored form, then you've got things that you can make those cancellations. So factor first. Again, the big mistake that I see most often is people saying, oh, I've got an x squared here and an x squared here, so I can just cancel those out. Oh, I've got a 9 here and a 9 here. I can just cancel those out. That is not how fractions work. So hopefully by now you guys are hearing me when I say that. This is an entire group of things that's happening first before it's divided by x squared minus 9. I can't take individual things and cancel out with individual things down here unless it's in factored form. So let's go ahead and factor, which is why we spent time factoring last week. All right, let me rid of my parentheses. Okay, so we need to factor. So I'm going to make my area model. I can factor both the numerator and denominator here. So first of all, let's look at the denominator, because that's not a typical quadratic. That is a difference of squares, which we reviewed last week in our factoring video. So hopefully we know that x squared minus 9 is really x squared minus 3 squared. So that factors to x plus 3 times x minus 3. And then I need to focus back on my numerator where I'm factoring x squared plus 6x plus 9. So let's draw the area model and factor this. So I'm going to put my x squared down here, my 9 here, and then I need to figure out how to split my 6 x's between these two squares to factor this. And for that we can use an area or the diamond game. So they multiply, my two numbers that I'm looking for multiply to 9 and add to 6, and that would be 3 and 3, because 3 times 3 is 9, 3 plus 3 is 6. So that means when I'm filling in my area model, it'll be 3x here and 3x here, which means this factors to x times x here plus 3 and plus 3. So this actually is, going back up to our problem, x plus 3 times x plus 3. So the reason why we factor, because now I have, instead of adding terms, so this plus this plus this, now I've factored it, meaning I have this times this divided by x plus 3 times x minus 3. That's why, excuse me, that's why now we can do those cancellations, because I've got a product instead of adding and subtracting things. So I know that x plus 3 over x plus 3 is 1, and now I've got x plus 3 over x minus 3. Can we cancel anything out there? Can I cancel these x's? And hopefully by now you're saying, no, we cannot cancel those x's because those are in those parentheses. We can't cancel that. So this just leaves us with our final answer of x plus 3 divided by x minus 3. We can't simplify that anymore. We should state restrictions though. So again, restrictions come from our original, or you can look at the factored form. That's the easiest way to get the restrictions. So in terms of this one, we need to think about restrictions where either one of these factors equals 0. Because if this one equals 0, when I multiply it, it'll equal 0 no matter what. And same with the other way around. So either way, so if I'm looking where this dot is now, if x was 3 and I subtract 3, then I've got 0 right here. And when I took that 0 and multiplied by 6, which I would have here if I did 3 plus 3, then I would have 0 in the denominator. So that's my first restriction. X cannot equal 3. And there's another one. Even though we canceled this factor out, I still have to use it when I'm thinking of my restrictions because it was originally a part of my original expression. So this would be if x equals negative 3, this would be 0. So x cannot equal 3 or negative 3. So those are our restrictions on x. Okay, let's take a look at another one here. So example B. All right, so 2x squared minus x minus 10, another quadratic, divided by 3x squared plus 7x plus 2. We've got a quadratic over a quadratic, and they are not factored. So this is why I said in the last video, if you cannot factor yet, you can't move forward. So we need to be able to factor this in order to simplify it. So I can't take this x squared and cancel it with the x squared. I can't take the 2 over 3 and do anything with that. I can't do any canceling or simplifying until I've factored both the numerator and denominator. So that's why we spent some time on that last week. So before I can continue, I need to figure out, I'm going to write the space there because I want to write this as factors. So let's go ahead and start that factoring process. Let's see, I'm going to do this numerator, I'm going to factor that here. So I've got 2x squared down here, negative 10 here. Then I need to take this negative x and somehow combine two x terms here so that they add to negative x. Now is where we use our area model, and now notice that my leading coefficient here is not 1, it's 2, which means instead of writing just the negative 10 right here, I actually do 2 times negative 10, and I end up writing negative 20 here, and then negative 1, so the coefficient of x goes right here, as we saw last week, so negative 1 right there. So what I'm looking for are two numbers that multiply to negative 20 and add to negative 1. My possibilities for multiplying to 20, that would be 10 and 2, but I can't combine 10 and 2 to add or subtract to get negative 1. 20 and 1 also multiplies to negative 20, but they don't add to negative 1. 4 and 5 would combine to negative 1 if my 5 was negative and I added 4 to that, and negative 5 times 4 would be negative 20. So that is my answer for that. So negative 5 times positive 4 adds to negative 20 and or multiplies to negative 20 and adds to negative 1. So that means I would put negative 5x here and positive 4x here. Then we need to think about, how do I split my 2x squared? I know I'm going to have x on one side, or x on both sides to multiply to get the x squared. Where do I put the 2? Well, what would make more sense? Putting the 2 down here so that I had to multiply it by something to get negative 5, or putting the 2 here so that I had to multiply it by something to get 4. Since 2 easily multiplies to 4 when you multiplied it by 2, that's where I'm going to put this 2 right here is going to be right there. So now I know that when I have 2x here, that means this entry needs to be a 2. And this would be negative 5 up here. And then you just want to make sure that works. So 2 times negative 5 is negative 10. So now I have my two factors for my numerator. So we can go back and rewrite this as 2x minus 5 times x plus 2. So it's like we have an entire factoring problem, and all we've done is factor the numerator. Now I'm going to factor the denominator. So now I'm going to do this one, and I'll do that over here. Alright, so we've got 3x squared, and then 2 goes up here in the top right. And then we need to figure out, how am I going to split these 7x's between these two boxes? And that's going to be determined from this diamond game. So our two numbers are going to add to 7, but we want them to multiply, not to 2, but to 3 times 2, because my coefficient is 3 out here. So that would mean I'm putting 6 right here. Two numbers that multiply to 6 and add to 7, that would have to be 6 and 1. 6 times 1 is 6, 6 plus 1 is 7. So that would be 6x here and 1x there. Then we're thinking about how do I arrange the 3x times x. So my x times x is going to go out here, but which side will have the 3? We'll think about which one of these is easier to get when you multiply by 3, and that would be this 6x. So I'm going to put that 3 right here, which means 3x times 2 is 6x, and then x times 1 is x. So here I have my two factors for my denominator. So that would be 3x plus 1 times x plus 2. How convenient. So when we factored both of these, we see I have an x plus 2 factor in the numerator and denominator, which means I can cancel those out because that equals 1, which means the result, my final answer here, when we look at 3x minus 5, or 2x minus 5 and 3x plus 1, there's no canceling I can do here because, again, this whole thing is divided by this whole thing. I can't cancel these x's. So my final answer is 2x minus 5 over 3x plus 1. But we need to write restrictions on x. My one restriction is going to come from this. This whole thing cannot equal 0. So if 3x plus 1 cannot equal 0, subtract 1 from both sides. Let me get some more space here. Alright, so 3x plus 1 cannot equal 0, which means 3x cannot equal negative 1, which means x cannot equal negative 1/3. So my restrictions would be negative 1/3. Don't forget, though, this is also going to give us a restriction of negative 2. So x also cannot equal negative 2. Okay, one final example here. Alright, so our final example, this example is just to show you that we don't always have to factor in that way that we just did in the last two examples. So let's see, I had x squared plus 4x over 2x plus 8. So our numerator is quadratic, but it doesn't have that last term. It would be plus 0. You can factor that using the area model that we've done up here, but we don't have to because there's only two terms here. But notice that each of those terms has an x, so that would be that greatest common factor. So again, that's why step one when you're factoring is always, is there a greatest common factor? Because if there is, you can just factor that out. So I can factor an x out of x squared, and I'm just left with x. And I factor an x out of 4x, and I'm just left with 4. So that's how my numerator factors. In the denominator, it's not a quadratic, but there's definitely a common factor of 2 because we've got 2 and 8. So when I factor a 2 out, my result is x. When I factor a 2 out of 8, it's 4. So I factor both of these, and I'm left with x times x plus 4 divided by 2 times x plus 4. So we can cancel out these x plus 4s, and we're left with x over 2. We do have that restriction, though. So think about what x cannot equal, and that would be whenever this whole thing equals 0, which would be when x equals negative 4. So x cannot equal negative 4. So I just wanted to throw this one in here just to reiterate that, yes, we do need to factor, but we don't always rely on area models. If our quadratic doesn't have that third term, you can just factor the x's out. Don't forget about factoring out those greatest common factors. All right, so that's it for this section. You guys should be ready to roll for that assignment on simplifying rational expressions, and I'll see you next time.